John, could you please share your screen? So while I'll give you a short introduction.
I think I am sharing my screen, but I'm not totally sure. Are you seeing a black screen being shared? This is
yes,
like,
yes.
okay.
Yes.
Let me,
Okay.
do you see slides?
Cool. Yeah.
Okay, cool.
So, cool. So I think, so Dr. Jon Barron is a staff research scientist at Google Research, and he works on computer vision and machine learning. So at Google, he has worked on several very cool products like Portrait Light, a lens blur, and the Google Glass. He did his PhD at UC Berkeley and advised by Jitendra Malik, and funded by the NSF Graduate Research Fellowship Program. And he received several very distinctive recognitions, like the C.V. Ramamurthy Distinguished Research Award from UC Berkeley, and also the Pammy Young Researcher Award, and also I think 2 Best Paper honorable mentions at ECCV. And I think everyone knows his recent work, NeRF, and that's here the exciting development.
Cool. Thanks, Cheng, for the nice introduction. Hi, everyone. Thanks for the invitation to speak. First, is my audio okay? Are the slides? You're seeing the slides and not presenter notes, right? Because I have no idea what's being shared right now. I'm kind of flying blind. Is everything?
Yeah, all looks good.
Okay, cool. Yeah, I work at Google, so I only know Hangouts, and I use Zoom 4 times a year. So I'm a little, yeah. I'm hoping to keep this kind of casual, so please feel free to interrupt with questions or whatever if you want to talk. Are we running 5 minutes late? Should I aim to end at 3:05, or should I try to end at 3 o'clock?
I think it's fine. We can say extend the next oral session by 5 minutes. Yeah.
Okay, cool.
Take your time.
Sure. Okay, so I'm going to be talking about NeRF. NeRF. I guess a lot of people have seen this content by now or are kind of familiar with it, but I'll just do a brief overview of what NeRF is, and then we'll get into kind of more extensions and applications that have a kind of creative focus, I think. So NeRF stands for Neural Radiance Fields. Neural because there's a neural network, radiance because the neural network is modeling the color and density of stuff, the radiance field. And field here kind of means in a calculus sort of sense of a continuous quantity that exists out in space. And this is in the scene representation line of work where a neural network is kind of memorizing and overfitting a scene, and we were using it for view synthesis. That's the title. That's what NeRF means. So the problem that we were originally trying to solve with NeRF is this problem of view synthesis. So on my screen, I'm seeing a series of still images on the left and a beautiful interpolated movie on the right. Is that coming through? What's the frame rate of this video? Could someone tell me?
We see that about 5 frames a second, I'm afraid.
Oh, okay. So the same. Okay, that's fine.
Sorry.
Yeah, whatever. This is the world we live in. So feel free to click that project page there, or type it in and open up. Take whatever other tab you're browsing right now and direct that page if you want to see some really nice animations. And throughout the talk, I'm going to speak as though you're seeing beautiful, wonderful, nice, smooth animations on screen, and you'll just have to take my word for it that is indeed what's happening. So NeRF takes a series of sparse images and learns a model, really optimizes a model from those images, and then it lets you generate new views of that scene, and they look really good. At the core of NeRF is a neural network, a very boring neural network that takes 5 numbers as input. So this is x, y, z, a point in space, and theta phi, which is the viewing direction, the angle that you're viewing that point in space. You can forget about view direction, though. Just think of x, y, z. And then there's very boring non-convolutional MLP. It's just 9 layers, 256 channels, reload activation. It really doesn't matter what it is, just a boring neural network. And the output is 4 numbers. That's RGB, color. So the color of that point in space, and density, sigma, which is from 0 to infinity. And that is how dense that point in space is in a volumetric sense. And this neural network, we're just going to repeatedly ask it, hey, here's a point in space. What's the color? How dense is it? And it will give us an answer. And this neural network is wrapped inside a ray tracing engine. This is kind of like a very straightforward ray tracer where we have cameras. We assume we know the pose of the cameras. They're given to us by stereo or by some other source. And for every pixel in the image, we're going to shoot a ray from the center of projection of the camera, from like your eyeball, out through the center of that pixel and then out into the world, and it will travel out. And we're going to draw samples along that ray, just evenly sample it with and draw discrete XYZ coordinates, take them, put them into a batch, send them through the network, and the network will give us density and color as output. And then with those densities and colors, we can just do standard volumetric rendering where we alpha compose from the back of the ray to the front. We just kind of walk from the back of the ray up towards the image. And if something is dense, it occludes the stuff behind it. And you just keep going until you've marched back up to the image plane, and then you have a color. And that's the color of that pixel. That's how you render a pixel. To render an image, you do that for every pixel. And that's what you do if you had to train to NeRF. The way you train a NeRF is you initialize theta to be random, and then you just repeatedly render the scene using this procedure and do gradient descent to minimize the difference between renderings and the input image. That's all you do, just per pixel mean squared error. And the weights of this model end up encoding the density and radiance of the field, like the color and the geometry of the scene. And that's all they do. They're just memorizing this one world. There's no notion of we're going to look at some pictures of something and then generalize to pictures of something else. We're just trying to basically overfit to this one scene. And yeah, it works really well. Here are some results of this working on just images from around the UC Berkeley campus. NeRF produces really like photorealistic looking views. You can find some mistakes, but they're pretty subtle. Thin structures, glass, refraction. There's water in that glass. These thin leaves and all these irregular shapes are well modeled. That pond there, it's mirror-like. It just fakes the mirror by putting a copy of the world underneath it. It really, this works very well. And particularly if you compare it to the kind of previous state of the art in these kind of neural rendering tasks or in the kind of classic 3D vision task, there's a huge leap in quality here. And yeah, so NeRF, it's, you know, the world is kind of hidden inside these neural network weights. And some people call this an implicit model, which I think implies kind of that there's more magic than it is. I think it's a quite explicit model of density. Like it's a mapping from a coordinate to a density value. And so you can do things to them, like you can trace a ray and you can measure where it terminates. So you can just ask the model, like, what was the distance where this ray kind of hit the 50% opacity mark, and you can get a depth map out. And the depth maps look beautiful. They have lots of nice detail. Thin structures are recovered. There's none of the kind of edge fattening you're used to seeing in stereo sorts of results. And you can do cool things with these depth maps. You can, you know, insert objects and do weird kind of compositing and mash objects together and things like this. This isn't really something we've explored, but it seems like a really cool kind of space to play in, and something that we think will enable some fun applications in the kind of like creative space. Though I don't have very much to say about that because I'm not a very creative person. There's one really big problem with NeRF, which is that, I mean, there's several really big problems really, but one really big problem is that it's very slow to render from, because you render on a per pixel basis, and for each of those pixels you have to shoot a ray out and query a neural network maybe 100 or 1,000 times. So you'll end up querying a network, you know, millions, tens of millions, hundreds of millions of times to render an image. This is painful. So we kind of fix it. We have a technique where we can kind of take this neural scene and bake it into a more classic graphics-like version of the scene that you can run in real time. So feel free to check out that link there, nerf.live. There's a demos tab, and you can look at those scenes in real time on your browser. Your fan will spin up, your computer will get hot, but it does run at 30 or 60 frames a second. And there's other people who've done this as well. A shout out to Planoctrees and a paper called Fast NeRF from NSR, and a paper from KiloNeRF that does something, a paper called KiloNeRF that does something similar. So there's lots of ways to make these things fast. They're hard to train fast for now, but you can take these things and turn them into real-time graphics assets that you can use. Here's an animation of a recording of me playing with one of these scenes in my browser, just so you can see that I'm not fooling. And yeah, I mean, it's nice, it's real time, it's detailed. There's lots of non-Lambertian effects that are captured. It all holds up really well. So you can imagine the kind of applications that would fall out of this. Another limitation of NeRF that we've been trying to deal with to enable more applications, NeRF assumes that the world is static in many ways. One way which assumes the world is static is it assumes that if I look at one point in space from the same angle twice, that it will look exactly the same, of the same color. And this works in a controlled laboratory setting where I walk outside and I move my camera around an object on a table, but doesn't work in unconstrained collections of, say, in this case, like landmarks or these kind of in the wild photo collections, things you might find in Flickr. So this is a paper that we have here at CVPR this year, and this is our attempt at kind of addressing this issue. So we want to take as input unconstrained photo collections of landmarks. We focused on a small number of landmarks that are well documented in these data sets. And we want to be able to do view synthesis, of course. And to do that, we need to be robust to this appearance variation. But that appearance variation captures a lot of information, right? There's a lot of information that you would want to model and use as lights move and things change. So the goal of this was to be able to create new views of objects, but also new appearances to kind of model this whole appearance space of these things. And then you can do really cool stuff. So why is this hard? Lots of things are done to these images. Lots of things happen, right? The sun rises and sets, the weather changes, lights turn on and off. Some lights are inside the object themselves. These images might get post-processed by Instagram filters or things. They've been messed up in lots of ways. So there's a lot of variation in the appearance of these objects that you have to account for. And beyond appearance, there's a lot of other stuff that happens in these pictures, right? People will stand in front of them and pose for photos. Flags will go up and down depending on world politics, and construction will happen. Road signs will, safety signs will be put up and things like that. And we need to be robust to this. So I'm not going to get into details about how this model works, but the basic idea, and this is an idea that we've used several times now for other things, is we're going to invent embeddings for these models. Here we have an appearance embedding, and this is just like a low-dimensional vector that's just optimized during training. It's associated with one image. We have an embedding for appearance and an embedding for this kind of transient idea. And the appearance embedding can affect the coordinate of the appearance of embedding can affect the radiance, the color of the image, but it cannot affect the geometry. And the transient embedding kind of determines what areas in space we try to be robust to. There's a field of uncertainty that we then composite down to an image to allow ourselves to be robust to outliers. And you put these things together and you get a working system. So here's a comparison to NeRF. So NeRF's on the left there, and you can see, so NeRF is trying its best, right? But there's a lot of stuff happening in these images. There's people and things and signs, and every time there's a person in one of these images, NeRF has to kind of split the difference between that picture of that person and the idea of there not being a person. So it'll make a kind of ghostly version of that person there. And it's more subtle, but also because photos taken from the left side of this building are different from the right side on average, it will slightly shift the colors as you move through the scene. And NeRF in the wild, NeRF W is what we call this. It doesn't have these problems. It's able to kind of reject the outliers near the ground, kind of too aggressively. It basically just gives up on trying to recover the ground, but it recovers the landmark very, very accurately and produces wonderful renderings. And the appearance is static as we move the camera. But we're not just recovering like one model of the scene. We've basically recovered a family of appearances of the scene in these appearance embeddings. Here I'm just iterating through the appearances in the training set for each scene. And we can interpolate not just in views, but also in appearance. So here I'm moving the camera and also just interpolating between these codes, and you can see get these really nice sun rising and setting and things like this. And critically, the geometry doesn't change. Like the geometry is completely fixed. All that's changing is appearance, and that's a hard guarantee provided by our model, which is a really nice property. And we run this on, man, this video always freezes. These are like 4K videos, and Keynote does not like that. But there's lots of videos on the website of us running this on cool things out in the wild. Highly recommended, worth checking out. Here's another attempt at overcoming a limitation of NeRF to enable like a fun application. The goal here was to allow us to NeRF a person because this was done during COVID. You know, we focused on being able to NeRF ourselves. So taking selfies and turning them to NeRFs, we call them NeRFies, which is a cute, albeit weird name. And I should mention this is not the only work trying to do deformable neural radiance fields. There's many other papers. I think there's 7 papers that are doing this or that have done this over the last year. So they're in the corner there. Feel free to check them out. And the project page is cool. There's lots of good stuff there. So yeah, the goal here is just a casual capture. So we take a camera, we wave it around ourselves, and we get a video, and then we NeRF that. And it works. We can actually get really nice reconstructions, basically photoreal, and depth maps that accompany that. And this is really hard. NeRF does not work for this. This is what happens if you run NeRF on these sequences. You get these weird kind of planoptic garbage looking renderings because even if you're really good at sitting still, you will move a lot. If humans just move, like we move a lot, assuming that we're static, is a bad assumption. It's going to be violated very badly. This is someone here. Alex is trying his hardest to be stationary, but it doesn't work. So, I mean, the problem here is pretty straightforward, right? That you got two images of a person at two different times, and you grab one point here, the corner of his glasses, and you look at where they correspond in 3D. You shoot rays through them. They don't correspond to the same location. So the fix is that we define a canonical frame. We're going to say there is one Alex, and he's going to live in this one canonical frame, this one coordinate space, and all these images correspond to deformations of that. They're observation frames, but we can map them into this canonical frame and do our work there. So that's what that looks like. That's what we're trying to do. And the trick here for making this work, where we're going to introduce a second MLP that is, again, it maps from XYZ, but the output is a different XYZ coordinate. It's the coordinate in the canonical frame. And like in NeRF in the wild, we're going to have this deformation code, this embedding that corresponds, that's allocated to each individual image and can be optimized during training. And the code gets concatenated to the input, to the XYZ coordinates, and we train the weights, we train the codes, and at the end of training, we are able to, this deformation field basically warps each ray. So we shoot a ray through the scene, and each coordinate along the ray gets warped, and we end up with this bendy ray in this canonical space. And that addresses this deformation. And making this work in practice is hard. There's, of course, a fine optimization trick. There's like a rigidity regularizer, but you get those working and you're good. And it works really well. So here's Steve Seitz on the left. He's a really good subject for this because he's very good at sitting still, even though he does move slightly. But he also has wonderful hair for this. You can see the thin strands of his hair are reconstructed very nicely. Basically photoreal. Like, I don't really see anything wrong with this. On the right, Toby the dog, less good. Toby is a good dog, but he moves a lot, and there's some other issues with the sequence, I think, because it's outdoors. But still, we're able to recover even uncooperative subjects. And there's lots of fun applications beyond just moving the camera. Like, we can do whatever we want to the camera. So here's a dolly zoom. We're just moving the camera and changing its field of view. Works fine. Comes for free. So everything here is volumetric. This is all volumetric rendering. So if we just shoot rays and then terminate, a few inches behind the back of Kun Hong's head here, then we get an RGB and alpha value for every pixel, and we can just map renderings on top of any background. And they look great. They look really good. So lots of fun applications you can imagine here. But there's one really big problem with that NeRF's work, and it's that if we can move a little, but every time we moved dramatically, especially if we opened our mouths or something, it would basically look like a topological change, right? It had a really hard time figuring out that my head had a movable jaw with teeth inside of it. It was it was frustrating. So this is new work. This went up live on Archive, I think, this morning. The website's up and running. It's really fun. And the goal here was to fix this problem, and to basically, we're lifting NeRF into a higher dimensional space, where that higher dimensionality allows us to model topological variation, and that lets us do things like open and close our hands or our mouths, or do various other things. Here's Kun Hong. Here's the first author, intern of this paper. He's moving the camera and moving his face, and NeRF's on the right here reconstructs very badly. It does some crazy things to his mouth. It does not like that his mouth has changed this much, and HyperNeRF is able to be robust to that. It just works fine. Here we're just moving the camera. Later on, we can move his mouth. The key trick here, and this is not like a new trick, this is a very classic idea, is that if you want to model smooth topological variation in a two-dimensional space, for example, a way to do that is to lift the problem into a three-dimensional space, and then have a smooth function in that space, but slice it, and then you get these level sets of this function will be will vary topologically and smoothly as a function of where you are slicing. It's a very straightforward idea, very classic, and we're just applying it to NeRF with a few modifications in terms of how you slice, and we kind of make it fit. Yeah, the output is great. This is Ricardo. He's doing a lot of strange things with his mouth, and NeRF's really did not like it. Gave him this weird kind of pelican beak. That's what we called it. And his depth map is kind of messed up. And this is fine. We can do view synthesis while he moves his face, and everything looks pretty good. Another example. This is, again, the same sort of almost topological variation. It's very hard to model. This is technically not topological variation, but it's very hard to model if you try to assume everything is just deforming hands with lots of empty space between them, because the space has to shrink to almost nothing. And this works fine. There's lots of wonderful examples. This one I like because it's not just showing topological variation, but also transparency, because you've got this glass here and everything's working fine. It looks nice. This is my favorite. This is a 3D printer. Just doing its thing. I really like this one. Here's Kanhong's face. This is, so we've got this deformation part of this model, and we have the separate kind of ambient embedding, this embedding in a higher dimensional space. And here, this is a widget we have on the website. It's pretty fun to play with. You should check it out. We're just dragging it around, and this brings us to different points in this topological space that are then sliced into to make a NeRF, and it ends up just corresponding to kind of the parameterization, the family of different faces that he can make. And it's the fact that he can articulate his head and rotate and things like that are factored out into the deformation part of the model kind of naturally. And this seems fun. This seems like the sort of thing that could have fun, creative applications. There's no explicit kind of rigging of this, right? Like NeRF doesn't know what a face is. It's never seen a face before. It enters every scene kind of blind and just overfits to the images basically. So there's no meaning to these axes. There's no like rigging or things like that. But you can imagine kind of layering that on top. So that's fun. So one last extension to NeRF that addresses a fundamental weakness to it. We call this NeRV. This is an attempt to enable, to kind of lift NeRF up into the realm of inverse rendering and enable relighting on top of view synthesis, and also materialization, retexturing, like turning those hot dogs into gold. So yeah, NeRF is cool, but it has this like really fundamental weakness, which is that we've described the scene. NeRF describes the scene as basically a field or a set of points that just kind of glow. They glow and they have a color associated with them, and they block stuff behind them. But the color that each of these points is glowing is a function of a bunch of things, right? It's a function of the material of that point in space, and also the incoming light hitting that space, either from light sources or from other parts of the scene. And NeRF doesn't know any of that. It has no idea where these colors come from. It just knows that there's points in space and they glow. And this works well for view synthesis, but if you wanted to do relighting, like change the lights of the scene, you're stuck. The colors are already baked into the NeRF, and you could try to tease them out. We actually have another work on how to tease them out, but ideally you would want to kind of come at this problem in a way where you directly solve for a decomposed version of this problem that understands lights, understands material, and lets you re-render the scene. And you can do this. That you can just, instead of saying there's a color at each point, you can say there's a BRDF, a material model at each point that describes how light is getting bounced off of the surface. And that's a good first step. It gets you a lot of the way there, but it doesn't really solve the real problem here. And the real problem here is scale. So the world is lit by things, right? You're gonna have points in space. They're going to be lit by any number of lights. So you have this kind of combinatorial explosion, right? So if you wanted to render your scene with direct lighting, you would need to shoot a ray, and then from every point along that ray, you would need to shoot more rays to each light. And the really hard thing is that there can be stuff between each of those points and the light. So there's stuff in between that could block the light, and you need to model that. So you need to shoot a ray. That's already expensive. But then for every light, you need to shoot another ray. That's bad. That's now you got a quadratic explosion in the number of light sources you have. And then it's even worse, because for each of those new rays, you have to draw samples along those. And this gets intractable. It's like immediately intractable. You cannot do it. It already takes us 2 hours to train a model. This would take years or decades or just the end of the universe. So the problem we had here is like, how do we fake this? How do we use insights from NeRF to kind of make this tractable? And the trick is, I guess, kind of similar to the trick in NeRF, where we're just going to add neural networks and ask them for the thing we want. So in this case, what we do is we make a new neural network that we query with a coordinate and a direction, and we just ask it, if I were to start at this point and shoot a ray off towards infinity, how much stuff would I encounter before I reach kind of the skybox, like the outside world? And it will say 0.7 or something. And then you can just go straight to the light source and say, I'm going to take the light source times 0.7, and you're done. You don't need to shoot this ray and sample points along it. And the trick for making this work is that these quantities, these total transmittance quantities, are things we already compute during training accidentally when we shoot the main ray. So there's a supervisory signal kind of sitting around that we can just use, and we use it. So that's good. We can do direct lighting. We can now have points and light sources. But the problem is still very hard because there's also indirect illumination, right? So there are lights. The lights will shine light on things in the scene, and then it will bounce off of those things and then hit the point that you're considering. So there's now this like quartic explosion. There's now like way too many rays you have to consider. You have to, for every point along your ray, you have to shoot a ray, hit something, and then shoot a ray at the light source. It's completely intractable and very sad. So the trick for this is basically we train another MLP. There's another network with another set of weights that for every point in space and for every, I guess I can back up one slide. For every point in space and for every direction, we ask it, if I were to shoot a ray here, where would I end up on average? Like, what is the distance that will get me to basically the next surface? And it'll say, oh, it's, you know, like 3 meters. And we say, thank you, neural network. And we just jump straight to that point. And then we query the other network I described that tells us how to get from a point to a light source. And we say, if I shoot off to that light source, how much stuff will I encounter? And it says 0.7, and then we're done. And now we can render a scene by, it's still a painful growth, right? Because we still have to shoot multiple rays for each point, and we have to query a neural network, which is not cheap. But now we're in the realm of the possible, where we can kind of shoot, you know, a handful of secondary rays and quickly shoot rays to the light. And now this becomes tractable. We can train it in a day instead of a million years. And it works. We can do relighting. We can get albedo maps, surface normals. We can change the lighting, change the materials. It's not perfect. There's kind of this characteristic bumpiness that is, it may be a bug, but I think it's kind of points to a fundamental weakness of this algorithm. But this is a long, you know, research trajectory because inverse rendering is a hard problem. That's basically what we're doing now. I think this is a really exciting step. And yeah, there's lots of nice, here we're querying points in the world and asking the neural network to tell us what the visibility and the indirect illumination are for that point in space, which you can visualize as environment maps. It takes a while to learn how to read these things, but they're pretty cool once you figure it out. And yeah, our results are not perfect, but they're very strong compared to like kind of naive baselines where you don't try to reason about indirect illumination and lighting and just try to train networks that just predict shadows and colors, which is what you're seeing on the left. So a really nice set of progress there. And that's all I've got. Thanks, everyone.
Okay, cool. Yeah, thanks for the great talk and very exciting results. And we have several questions in the chat. And so the first one actually starts from some comment. NeRF is a huge step forward for view synthesis, and the whole community is excited about it. And it's great work. And so the first question is, first of all, partially transparent scenes. Volume rendering is clearly necessary to synthesize photorealistic images.
Yeah.
For fully opaque scenes, so what is your intuition for why the volumetric formulation is important?
Yeah, that's a good question.
Volume rendering formulation is differentiable, so it facilitates training.
Yeah, that's it. I mean, it's really, the fact that this is volumetric rendering is almost accidental. We very rarely deal with volumetric subjects. I mean, sometimes the model fakes complicated things using volumetric effects like hair. You know, hair isn't actually volumetric, but it's a good way to model it. The real reason for this volumetric stuff is that it's just wonderfully well behaved in terms of optimization. And or another way of thinking of it is not volumetric rendering, like raster-based rendering, where you have a polygon soup or a mesh of triangles or whatever, is horribly ill-behaved for gradient-based optimization. It's really, really hard to make that work. And people have done really good jobs of making it work, but it's if you just imagine the problem of taking a polygon soup and turning it into a person's face, it's like there's dead gradients everywhere, occlusion and things like that. It's just, it's really, really rough. And the volumetric rendering, if you write it down in PyTorch or JAX or whatever, you'll see that it's a bunch of sigmoids and soft pluses. Like it's perfect. Like it's exactly what you want it to be. All the gradients will die if something becomes like very opaque. You will kill a gradient, but it's very hard to do, and that's the trick.
Okay, yeah, I think the second question asks about your intuition about recent methods that attempt to explicitly decompose a larger scene into, say, a grid or many NeRFs.
Mm-hmm.
So are these kinds of explicit spatial decompositions necessary? Or do you think it should be equivalent to simply allocate all of the network capacity to one giant NeRF for the whole scene? So I'm bullish about this explicit spatial decomposition.
Yeah. I think that all the spatial decomposition techniques I've seen, I don't see any reason why they would be qualitatively different from a single monolithic model, because you can have a giant MLP that basically switches and like routes you down different paths. And that's kind of what happens under the hood. But I think there's a huge win in terms of speed. I mean, like the killer NeRF paper is like 1,000 times faster than NeRF. This is like that's a big deal. Like speed is really important. Like being able to train these models really fast is a big deal, and it's important for scale and for progress and everything. So I think that this idea of spatial decomposition is an important one. I think it's important primarily because of speed, and I think speed is very important. I could imagine a story where the decomposition is also important because of things like regularization or priors or amortized inference. That seems possible. I haven't seen any results that suggest that, and I don't have any strong intuition one way or the other on that.
Mm-hmm. Yeah, I think there's another question is, so can we use multi-view images or scene generated by using image synthesis GANs, so without explicit camera parameters as input, to train NeRF W or any of the NeRF models you mentioned?
Well, images generated from a GAN, I mean, the best images from the best GAN, if you generate a lot of images of that thing, it usually doesn't correspond to a physically coherent object, right? If I keep asking for Barack Obama's face over and over again, and then I try to do structure of motion on that, I wouldn't expect that to work. Like I wouldn't expect there to be like one 3D model that they're all rendering. And we can kind of see that from work like PyGAN, like there are these papers that kind of take NeRF and embed it into a GAN, or kind of build this hybrid system where you synthesize a NeRF, and then you get renderings that are like geometrically coherent, because they have to be, because they're all just renderings of the same volumetric cloud. Those, if you then NeRF'd those images, that you would get a 3D world out. But if you don't have that kind of guarantee on the synthesis side, it's hard to imagine how you would then be able to use that for kind of 3D multi-view stuff at the end of it.
Okay, cool. Yeah, I think, thank you. There's maybe one last question. Yeah. So recent methods on novel view synthesis build 3D reconstruction and rendering functions that is view dependent and show performance somehow similar to NeRF. So what do you think of this direction?
Well, I mean, sorry, Abdullah, can you reference a paper in particular? Because I mean, I would say NeRF is also building a 3D reconstruction and learning rendering functions that are view dependent. I mean, you're talking about like proxy mesh things, or?
Yeah, I think maybe like maybe you can follow up in the chat. Yeah, let's
sure.
I think we are kind of running out of time. Let's go to the oral session, and
okay.
Yeah, I will handle it to Kalyan.
Thanks, everyone.
Yeah, thanks for the great talk.
Thanks, Jon, and thank you to all our invited speakers for their great presentations. We'll now be moving on to the two oral talks in this session. And the first one is high resolution complex synthesis with transformers by Manuel Jan, Robin Rombach, and Bjorn Omer. And Manuel, I think